Hello guys. Up to now, what we have discussed in the last class. In the last class, we have discussed about we started the chapter number 6. Okay, and we have started chapter number 6 and we discussed about the scalar products. Okay, scalar product or dot product of scalar product or dot product. Okay, so first thing today in today's class, I will discuss about a problem regarding the scalar product. Okay. Here this example is given in your NCERT textbook. Suppose we have two vectors. Okay, A is equal to 3 I cap plus 4 j cap minus 5 k cap, and B is equal to 5 I cap plus 4 j cap plus 3 k cap. Okay. Now we have two vectors A and B, and we are asked to calculate the angle between A and B vector. Okay, to calculate the angle between A and vector, and also projection of A. Okay, we are asked two questions from here: angle between vector and vector B and projection of A on B. So how we proceed in such problems? See, we know what is dot product. A dot B is equal to how much? Magnitude of A vector, magnitude of A vector B vector into cos of angle between the two vectors. So from here, what we do? A dot B is how much? Okay, first we take the left hand side. Okay, A dot B, from here A dot B will be how much? Like we have done in the last class, it will be product of the x component of both the vectors, then plus product of y components and plus product of the z components of both the vectors. Okay, so it will be 15 plus 16 minus 15 equal to 16. Okay, so product of dot product of A and B vector is 16. Now you have to calculate this part. Okay, so see, magnitude of A will be how much? Okay, magnitude. So similar, since we have in the last class we discussed that. Suppose we have vector P. The magnitude of this vector is nothing but the root over the square of root over of the sum of the square of this component plus pz square. So it will be root over 9 plus 16 plus 25 is equal to root over 15. Similarly, magnitude of vector B will be 25 plus 16 plus 9 is equal to root over 15. Okay, now we put this and this into this expression. Okay, so what it will be? A dot B is how much? 16 is equal to magnitude of vector A root over 50, magnitude vector B root over 60 into cos of theta. Theta is the angle between A and B. We are asked to calculate the theta. So cos of theta will be how much? 16 to 15 to 50 root over 15 to 50 will be 50. So theta will be how much? If we solve this, 0.3, theta will be cos inverse 0.32. Okay, so this is the angle between A and B. Angle between vector A and vector B. Okay. Now projection of A will be how much? Projection of A on B. Projection of vector A will be A cos theta, or theta is how much? Magnitude of A, this is over 50. then cos of theta is 0.16 by 50 is 0.32. So 0.32. So if we solve this, what do you get? 50 into 0.32. So 2.36. 2.36. Okay. So this is the projection of vector A on B, and this is the angle between the two vectors. Okay. This is how we solve the problems or proceed for the problems regarding scalar products. Okay. So by using the concept of scalar product, we can determine the angle between two vectors. Okay. From that angle, we can easily calculate the projection of one vector upon another. Okay, this type of things. So now next topic is work energy theorem. Theorem by Newton. Okay. See, in this theorem, work and energy, these two physical quantities are combined or are related by a single theorem. Okay, by Newton's work energy theorem, these two physical quantities, work and energy, these two physical quantities are combined in a single formula, a theorem. So what is a theorem? Suppose there is an object of mass m moving with a velocity u, initial velocity, and after covering a distance s, the velocity of this object becomes v. Okay. Suppose there is an object of mass m is moving with an acceleration. The object of mass A is moving with acceleration a. Initial velocity of this mass m is u, and after covering a distance s, the velocity of the mass m becomes v. Okay. So from this system, you can write the equation of motion of this object is v square minus u square equal to twice as, like we have obtained in the earlier classes. Okay. So from here we can write this. Okay. Now see, v square minus u square equal to twice as. Okay. A is the acceleration and s is the distance covered. Okay. V is the final velocity and u is the initial velocity of the object. Now multiplying both sides by m by 2. So what we get? Half of m c square minus half of m c square equal to twice m a into s. Okay. By half by 2. So what we get? Half of m v square minus half of m u square is equal to, see, 2 and 2 will be cancelled, ma into s. See, from Newton's second law, what we get? Ma is the force. Okay. Ma is the net external force. Okay. Net external force, and s is the displacement of the object of mass m. Okay. See, this is a so this is nothing but what? This is the work done. Okay. I'm using from the concept of vectors. I'm using that, and I'm writing this f dot s. Okay. F is a force vector and s is the displacement vector. Okay. And product of these two is a scalar quantity. The product of these two is scalar quantity, which is the another physical quantity, which is work. Okay, so I'm writing this term like this, okay, in terms of vector. So see, half of mv square, it is nothing but the kinetic energy of the moving object. Okay, so v is final velocity, so this is the kinetic energy of the object. This is the final kinetic energy of this object of mass m minus this is initial kinetic energy, and f dot is nothing but work done. Okay, work done on the body of mass m by force f in displacing that object a distance s. Okay, so this is the work energy theorem, or you can write the change in kinetic energy is equal to the work done on the system. Okay, so from here we can write that from here what we get, the change in kinetic energy. Okay, change in kinetic energy of a moving body is equal to the work done by the net force. Okay, so from here we can write change in kinetic energy of a body is equal to the work done by the net external force. Okay, so this is the work energy theorem. What is the statement of the theorem? That is, the change in kinetic energy of a body is equal to the work done by the net external force. Okay, so see, this is a mathematical expression of this statement. The change in kinetic energy of a body is equal to the work done by the net external force. Okay, so this is the work energy theorem, Newton's work energy theorem. Okay, see, kf minus ki is equal to w. Okay, in this theorem there are two physical quantities which are related by this theorem, or which are combined. First one is work and this is energy. Okay, in this theorem work and energy are combined with some physical law. Okay, by this work energy theorem, work and energy, which are two different physical quantities, are combined in a single law. Okay, so see, like we have discussed, or we have studied in the earlier, that if that in a physical law, okay, in this type of physical law, all the quantities, okay, all the quantities must have same dimension for the validity of this formula. For a validity of the for a formula to be physical relation, or formula to be valid, there is essential condition that all the quantities, okay, all the quantities must have same dimension. So the dimension of work is what? Force into displacement, that is m L square t to the power minus 2. Okay, so see, from here we can say that the dimension of energy, here is kinetic energy actually, or you can say dimension of energy is also m L square t to the power minus 2. Okay, so dimension of work and dimension of energy are both same. Okay, now the SI unit of work, okay, it is joule, or CGS, in CGS unit is how much? It is R. Okay, so joule means what? Joule means kg meter square per second square, and arguments are gram centimeter square per second square. Okay, gram centimeter square per second square. So 1 joule is equal to how much R? Okay, you can calculate. Okay, so see, 1 joule is equal to how much? Kg meter square per second square. So 1 kg will be 1000 gram. Okay, and 1 meter is 100 centimeter. So 100 square into centimeter square per second square. So it will be 1000 into 10 to the power 4 gram centimeter square per second square. So it will be 10 to the power 7. This is nothing but R. Okay, so 1 joule is how much? 1 joule is equal to 10 to the power 7 R. Okay, so this is the relation between the SI unit and serious unit of work. When I discuss about the work, about the energy, okay, work is nothing but energy. Unit of energy is also same. That is joule. Okay, unit of energy. Unit of energy is also what is it is SI unit of energy is also joule. Okay, but in physics, in different branches of physics, we use different units of work. Okay, in different branches we need different units of work. Okay, this dimension of this units are same, but we use but the form is different. Okay, the form of the energy is different. Okay, so another unit of energy is electron volt. Okay, so what is electron volt? It is the what is 1 electron volt? It is the kinetic energy gained by a single electron while accelerating through a potential difference of 1 volt. Okay, so when we discuss about the energy of an electron in a orbit, okay, in terms of atomic and molecular physics, okay, we define the energy. Okay, we define the energy of an electron, or we express the energy of an electron in terms of electron volt. Okay, and 1 electron volt is how much? It is the kinetic energy gained by a single electron while accelerating through a potential difference of 1 volt. Okay, so 1 electron volt is how much? 1 electron volt is how much? 1.6 into 10 to the power minus 19 joule. Okay, 1 electron volt is how much? 1.6 into 10 to the power minus 19 joule. Okay, so when we discuss about the, suppose this is the atom. Okay, this is atom, it is nucleus, and 1 electron is moving around the nucleus. Okay, so energy of the electron, okay, in this orbit, okay, is expressed in terms of electron volt. Okay, and 1 electron volt is how much? 1.6 into 10 to the minus 19 joule. Okay, so it is very small amount of energy. So in such cases, okay, in atomic and molecular cases, we use the energy related to a electron, okay, or subatomic particles as electron volt. Okay, we express the energy of electrons and subatomic particles in terms of electron volt. Okay, 1 electron volt is 1.16 × 10 minus 19 joule. Now, if there's another unit of energy, which is calorie. Okay, then 1 calorie is how much in terms of thermodynamics. Okay, in terms of thermodynamics, when we discuss about the heat energy, the term calorie comes. Okay, in thermodynamics, when we discuss about the heat energy, the term calorie comes. Okay, so in different form of energy, okay, in case of so in different forms of energy, use different unit of the different units of energy. Okay, in different forms we use different form of, or we use different units of energy. Okay, but it is same energy but in different form. Okay, you can express one form into you can express or correlate one form to another form. Okay, like 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. Okay, so 1 calorie is how much? It is heat energy required to rise the temperature of 1 gram of water to up to 1 degree centigrade. Okay, so calorie is what? It is the heat energy required to rise the temperature of 1 gram of water up to 1 degree Celsius. Okay, so see, in this case we are discussing energy in terms of heat. Okay, in this case we discuss or we express energy in terms of heat. Okay, so 1 calorie is how much? What is calorie? 1 calorie, it is the heat energy required to rise the temperature of 1 gram of water up to 1 degree Celsius. Okay, so calorie is nothing but this is the temperature required to rise the 1 gram of water temperature. It is a heat energy required to rise the temperature of 1 gram of water up to 1 degree Celsius. Okay, so 1 calorie is how much? 1 calorie is how much? 1 calorie is 4.186 joule. Okay, so when we discuss about the calorie, when we discuss about the energy in terms of heat, okay, what we use the term? We use the term calorie. Okay, when we discuss heat, when we discuss energy in terms of heat, okay, when we discuss energy in terms of heat, we use the term calorie. Okay, so in terms of electron and subatomic particles, in terms of energy relating to electrons in orbit or in terms of subatomic particles, we can express energy in terms of electron volt. Okay, so in terms of charged particles, okay, in terms of charged particles like electrons and subatomic particles, we express energy in terms of electron volt. Okay, and in terms of heat energy, we express its unit in terms of calorie. Okay, so if we see the dimension, okay, electron volt, dimension of electron, it is same, nothing but ml squared e to the power minus. Okay, see, when we discuss about the dimensions, the dimension of electric potential, dimension of electric potential is what? work by charge. Okay, work by charge. Okay, so electric potential is nothing but V. Okay, voltage, or work is the form of or work, you can say energy, both have same dimension, and charge is Q. Okay, see here, if you multiply Q into V, what we get? We get the dimension of work. Okay, so work is what? Q into V. So see, this is charge of electron and voltage. So this is nothing but work. Okay, the dimension of electron hole is nothing but dimension of energy, m L square T2 minus 2. Okay, so these are the different units of energy. Okay, now where we are, so suppose, and here mainly in mechanics we use the unit joule. Okay, in mechanics we use the unit of work as joule. Okay, so what? Okay, suppose I have an object. Okay, suppose I have an object and a force is applied in certain directions. Okay, due to this force, this object displaces after distance d. Okay, the force is applied at a certain direction with the horizontal or with the displacement. Suppose angle is theta. The force F is applied at angle theta with the displacement. Angle theta with the displacement. So, what is the work done in this case? Work done. So work done is nothing but F dot D. Okay, and F dot D is nothing but F means F dot D means F cos theta into D. F cos theta is what? It is the projection of F in the direction of D. Okay. F cos theta is nothing but it is the projection of F. Projection of force F vector in direction of displacement of D. Okay, and D is the displacement. Okay, so F of work done, what we get? Work done due to the force F is what? Cos theta into D. Okay, so work done due to this force. Work done due to this force is what? F cos theta into D, or F d cos theta. Okay, so we can say that work done. So from here we can say that we can conclude that work done by a force is the product of the component of force along the direction of displacement with the magnitude of displacement. So from here, how to conclude that work done by force F on a system or on a body is the product of the component of force. Okay, product of the component of force is cos theta. Okay, product of the component of force along the direction of displacement. Okay, see, along the displacement, along the direction of displacement, what is the component of force? That is, component of force is the projection of F on displacement vector D, which is F cos theta. Okay, so work done by force is the on a body is the product of the component of force along the direction of displacement. Okay, with the magnitude of displacement. Okay, that is F cos theta into D or FD cos theta. So this is what? This is a mechanical work. Okay, this is the mechanical work done on a system or on a body. Okay, this is how we express a mechanical work done on a body or system. See, there are certain cases. Okay, there are certain cases relating to this type of system. Okay, so first case is what? Suppose a person is holding a mass m. Okay, and the person is at stationary position. Suppose a person or a man is holding a mass m. Okay, is holding a, and it is standing at this without any displacement or without any movement. Okay, that is the person is in stationary position. Okay, suppose a person is holding a mass m and it is in stationary position, then work done in this case is what? It is 0, because there is no displacement. Okay, if you hold suppose you are holding an object and you are in stationary position. Okay, there is no movement. Okay, suppose you are holding some object with certain mass and you are standing in the same position without any movement or without any displacement. So in that case, work done on the system, okay, will be what? Will be 0, because there is no displacement. U is equal to 0. Okay, there is no work done. For work done, there must be some displacement. Okay, on application of some force. Second case, suppose I am considering that there is an object of mass m is placed on a smooth surface. Okay, smooth surface, where coefficient of substitution is very less than 1 or it is very less. Okay, in these cases, what actually happens? In these cases, what actually happens? Because the smoothness of the surface, okay, smoothness of the surface, sometimes this mass or this body starts sliding. Okay, it starts sliding. Okay, due to the smoothness of the surface, what happens? The mass starts sliding on the surface. Okay, so in these cases, so what happens? After some time, it covers some displacement. Okay, so sometimes what happens? It covers some displacement or covers some distance. Okay, by sliding on the surface. Okay, so in these cases also, work done is 0. Okay, because work done is what? F dot D. Okay, if there is no external force, F is equal to 0, then work done is also 0. Okay, in these cases, see, there is a finite displacement. Okay, there is a finite displacement due to the sliding of the body on the smooth surface. Okay, but there is no external forces applied on this body. Okay, so though it covers a certain distance or there is certain displacement, in this case the work done is 0 in this case. Okay, because there is no external forces applied on this body. So in these two cases, we will consider the work done on the system is 0. Okay. The third system is that if force and displacement are perpendicular to each other. Then what happens? Work done is 0. Okay. If force and displacement vector are perpendicular to each other, then work done will be what? Work done will be 0. Okay, because see, work done is what? F dot D, or you can write F D cos theta. Theta is 0. Theta is 90 degree. Theta is what? In this case 90 degree. So that can be perpendicular to each other. So F D cos of 90 degree or 0, or W is equal to 0. Okay. In case of in case of force and displacement are perpendicular to each other, the work done is always 0. Okay. I am giving an example for this. Suppose there is a body, okay, body of mass m moving in certain direction. Okay, it covers some distance. Okay, so what forces? Suppose a body of mass m is moving in a horizontal plane. Okay, it is a horizontal plane. The body is moving in a horizontal plane. Okay, a body is moving in a horizontal plane in certain direction. Okay, so what are the forces applied on this body? The forces are in this direction. There is a force F. Suppose it is moving due to the application of force F. Okay, so also in the direction of displacement there is a force F. Okay, and another force is mg. Okay, gravitational force or gravitational force. Okay, so in this system or in this body, what are the forces applied? F and Fg. Okay, so and see, displacement of this object is in which direction? In this direction. Okay, this is the direction of displacement. So see, when we calculate the work done, what we write? F dot D. Okay, there is no effect of gravitational force. Okay, mg. Okay, there is no effect of mg in this case. Okay, we only write work done is equal to F dot D. There is no effect of gravitational force in this system. Okay, because so why? Because see, this is direction of displacement, this is the gravitational pull, and they are perpendicular to each other. Okay, angle between them is 90 degree. So this is an example of that when displacement and force are perpendicular to each other, work done will be what? 0. Okay, there is no effect of gravitational force during in the work done in this system. Okay, work done in case of work done in this system, there is no effect of gravitational force. Okay, so this is an example of 0 work done. Okay, when force and displacement are perpendicular to each other.